Hello, welcome back. This is Calculus 2. We're looking at 6.2. We're working with differential equations. And our first model is the growth and decay models, which you probably have seen before, exponential growth and exponential decay. We're going to kind of obtain those models by solving a differential equation. Okay. So first we need a little bit more work with just solving differential equations, and we have a whole section dedicated to this called separation of variables. We'll see that in the next section, but I just want to kind of introduce it already because it's kind of needed. So solving differential equations, kind of an intro. I think maybe I've already introed this already. It's basically you just integrate. So a simple example, dy with respect to d, I guess x, I need an x, not a t. dx equals x plus 3. Okay. So all you're doing is integrating both sides with respect to x, but you can think of it as kind of just in a different way, separating. Okay, multiply both sides by dx. I mean, literally, it's not what you're doing, but it's what you're going to be writing. Okay. Actually, you're integrating both sides with respect to x, and kind of like the chain rule gets rid of the dx on the left. But this is the way we generally will write it when we are working. So on the left, you have the integral of 1 dy, which will end up being y. And then on the right, you have the integral of x plus 3 dx, which will be x squared over 2 plus 3x plus some integration constant. Okay, and that's it. Let's look at one more. Y prime is equal to square root of x times y. Okay, so the deal is to get all the y stuff on one side, all the x stuff on the other. And y prime is the same as dx over dy. It's just a different notation for it. You could rewrite square root of x is x to the 1/2. So I'm going to multiply both sides by dx and then divide both sides by y. Okay. And what you end up with then is dy over y, and on this side you'll get x to the 1/2 dx. And then you just integrate both sides, and you end up with, on the left, ln absolute value y, on the right, the power rule, so 1/2 plus 2/2 is 3/2, divided by 3/2 is 2/3, plus c. And what you're generally after is an explicit solution. Okay, it's not always possible to get an explicit solution, but in this case it is. And the way you do it is by exponentiating both sides. Okay. On the left, then, the e and the ln kind of cancel, and you have the absolute value of y. On the right, what you want to begin doing is kind of splitting up the exponential into two parts. Remember, if you have a to the x times a to the y, that's equal to a to the x plus y. And what I did here, going from here to here, is kind of the reverse operation. So I began with e to the, and this is going to look ugly, 2/3 x to the 3/2 plus c, where everything's in the exponent, and then I just split it up. And so instead of going like in this direction, I went in this direction, right? So I'll end up with e to the 2/3 x to the 3/2 times e to the c. Okay. Then I can drop the absolute value. I'm going to swap the right side using the commutative law of multiplication. I could put the e to the c first. And then I'll have e to the 2/3 x to the 3/2. Dropping the absolute value signs, I can replace that with a plus or minus on the left. And that's just, if you remember, that's kind of a general rule for solving absolute value equations from pre-calc. Okay. Okay. What I'm going to do next is just replace this thing with a constant. I have to be a little careful because this thing technically can't be equal to 0. But if you look back at the original equation, y equals 0 is a solution to that differential equation. Y equals 0. The derivative of y would be 0. And then if you substitute in, you have square root of x on the left-hand side times y equals square root of x times 0 if you do the substitution, which equals 0, which equals y prime, which is the left-hand side of the differential equation. Oops, y squared y prime. So y equals 0 is a solution. So you could just replace that with a constant. Okay. Recall that any exponential like e to the x will never equal 0. So that's the issue that I was kind of grappling with. If you didn't really catch what I was talking about, this thing in red technically can never be 0. Okay, there's no c value you could put in there to make that 0. But when you replace it with general c, now you're kind of saying, well, it can be equal to 0. And what I'm saying is that's okay because 0 is a solution to the differential equation. And I prove that right here. Okay. For you guys, generally you'll just say, okay, I can replace this plus minus thing with this big constant c, and you kind of forget about all the other junk after a while. Okay, so that's the kind of the important process that we need, this type of differential equation method that we're going to need to produce our exponential growth formulas. So here we go. Section 2, growth and decay. These are the formulas that you'll see in physics or chemistry with regards to radioactive decay. You'll see them in biology with respect to exponential growth. And it's kind of the cheapest mathematical model you can get your hands on. It's not very realistic. But anyways, it's what this differential equation is saying, and you could build your own differential equations. There's nothing wrong with going out into the real world and building a differential equation. That's kind of what you're expected to do. You're expected to be creative, apply this junk. What does this thing say? We'll pretend y is some sort of population. It's saying that the rate of change of the population with respect to t, so this is kind of the rate of change of population with respect to time. Oops, I butchered the word population, I apologize. Is that equal sign, you read it as is. The k is proportional. Is proportional. So you remember, hopefully, from algebra or pre-calc, inversely proportional, directly proportional, those things, you could Google those if you forget about it, is directly proportional to the population at some time t. Some time t. Okay, this kind of makes sense. So, and you can think of it in terms of fruit flies, which maybe some of you studied in high school in biology. So you have like, a population of fruit flies, and the growth rate is proportional to the number of fruit flies you have. Right, so if you have, just some fruit flies over time, you're going to have more fruit flies, right? It's the rate of change of the population will be positive. If you have only one fruit fly, there's not going to be much of a rate of change, right? You're just going to end up with one fruit fly, if not 0 fruit flies, right? So it's if you have a lot of fruit flies, there's going to be growth potentially, and this is where it gets a little bit unrealistic, right? Because if you have too many fruit flies, you know, they're going to exhaust their food supply or whatever, and they're going to start dying off. They're not going to grow exponentially forever. You know, if you have 1 million fruit flies, it's not going to, it doesn't really imply that you're going to have 1 billion fruit flies over the next couple of minutes, right? And it's not realistic, but that's what I said. It's the cheapest model out there. And so anyways, let's go ahead and solve this and see what the actual equation is. So this is the differential equation for growth and decay. Let's see what the actual equation for growth and decay is, right? Okay, so we separate. I'm going to multiply and get the dt on the other side. I generally will keep all my constants on the right-hand side, and I've learned that just through experience. It becomes a headache if you try to move the constant to the left. So I'm just going to keep the k on the right. Okay, and I eventually end up with dy over y equals k dt. Okay, so then you kind of integrate both sides. You end up with the ln of the absolute value of y equals kt plus some integration constant. And then we're going to exponentiate both sides. So e to the ln absolute value y equals e to the kt plus c. And then we could start simplifying a little bit. So e and the ln cancel. We get absolute value y. I'm going to bust up the e to the kt plus c into e to the kt times e to the c. I'm going to drop the absolute value signs. I get a plus or minus, swap the e's, and then I'm going to replace this thing with a general constant c, and that constant will include 0, because 0 is a solution. Okay, so the rate of change of the population when you have 0 in your population is just going to be 0. So that would be kind of like what I guess they would call a steady state solution. I don't know. I don't remember. Anyways, let's see what this is. Oh, that's it. That's our exponential growth model. So one thing to note about this, C is always the initial population. You could tell that by putting in 0 for t, right? So if you have y of 0, y of 0 equals c e to k times 0, which will be 0, which will equal c times 1. So the initial population is that c value. K is called the growth constant. And if k is negative, that just means the growth is going downwards. So you have exponential decay. So k is less than 0. You get exponential decay. If k is greater than 0, then you'll get the exponential growth. Okay, great. We want to look at the decay models. So after you get this equation, you're kind of done with the differential equations part, and the rest of the homework problems just become kind of what do they become? Kind of pre-calculus problems, right? Do you know how to solve an exponential equation and stuff like that? So anyways, let's take a look at some of these. So this is a typical kind of example where you're filling in a chart. And this is exponential decay for 226 radon. And they give us some information on the half-life, and they want you to fill in some blanks. Okay, so the half-life is 1,599 years. And they want you to figure out the initial amount. And then figure out how much is there after 1,000 years. And they give you how much is there after 10,000 years. Okay, so they're telling you there's 0.1 grams after 10,000 years, and you have to fill in the blanks. Okay, so we don't have to go and reinvent the wheel. We have our newly formed exponential decay model, CE to the KT, which you should have memorized for the test. And So what are we going to do? I kind of use the information to collect the variables, to solve for the variables. I'm chasing them down. So I need to find C and I need to find K. All right, so I'll begin with the half-life. So after 1,599 years, half of the original amount, so the original amount is C, there'll be half that amount left over. Okay, so when I plug in 1599 for T, I'll end up with 1/2 C as the output. Okay, I can get rid of the C value, assuming C is not 0, which it obviously is not, because there's, after 10,000 years, there's 0.1 gram left. So we'll end up with 1/2 equals e to the k times 1599. Then you could take the log on both sides, get ln of 1/2 equals ln of e to the k times 1599, and there'll be cancellation, so you just end up with 1599 k. So I just took the ln on both sides. And then solve for k. So k will equal ln of 1/2 divided by 1599. Okay. And generally you get like 4 decimals. I hate approximations, so I'm just going to keep that as my k value and use it in the formula. So we have y equals c e to the ln of 1/2 all over 1599. Okay. So next, I'm going to use the 0.1 grams to solve out for K, right? So I'm still kind of to solve for C. I just found K. Okay, so 0.1 will equal then C e to the ln of 1/2 all over 1599 times 10,000. And you could just solve for C by dividing by that e to the whatever. So C will equal 0.1 divided by that big ugly creature. So 0.1 divided by e to the ln of 1/2 all over 1599 times 10,000. And I get an approximation for that on my calculator. I'm getting approximately 7.63 grams, and that's your initial amount, right? So 7.63 grams. Then you have kind of your model with all the unknowns filled in. So at this point, you can just substitute in the 1,000 for T and figure out what you need to figure out. Okay, so your model looks like this now. And for the last part, you want to know how much is left after 1,000 years. So you just plug in 1,000. Okay, and I got approximately, what did I get? 4.95 grams. Okay, so it's really just a pre-calc problem. 5 grams. Let's look at the exponential growth version really quick. And you generally will see these types when you're working with investments. So if you go into banking, there is good work at Progressive. If you want to go into what do they call it? Insurance. And don't think insurance is boring. I had one of my students, basically all he does is work with visual representations of data at Progressive. Okay? And he works on their campus, and basically he's more of an artist at this point than a mathematician. So you just find ways to present data to people who study data. So don't think just because you're working in insurance that it's like this boring job. So there's a lot of jokes about people who work in insurance that they're boring and stuff like that. No, okay, there's plenty of stuff to do there. You can find something you like within your job. Okay, so anyways, here we are in a sort of a banking type problem. We're looking at an initial investment of $750. The time to double is, they're giving you 7 3/4 year for your money to double once you put it into some sort of bank account. 7 3/4 years. And they want to know how much you're going to have after 10 years. And we're using this exponential growth model, and it's basically continuously compounded interest. Okay, so first off, it's similar to the half-life problem, except instead of half-life, you have double life, kind of. So instead of setting it equal to 1/2 c, you're going to set it equal to 2c. Okay, so you have 2c equals c e to the k times the 7 3/4 years, but I'll rewrite that as 31/4. Okay. And then you can divide both sides by c, and then take the log of both sides, and you should be happy. So 2 equals e to the 31/4 k. Take the natural log on both sides, and you end up with ln of 2 equals 31/4 k. Multiply both sides by 4/31, and you get k equals 4 ln of 2 all over 31. Okay, and if you get an approximation, it's about 0.089. So your annual rate is going to be if you move the decimal over, 8.9%. Okay. Right. So then we want to know how long, or no, we want to know how much money we have after 10 years. And they gave us the initial amount, so I didn't have to use C or anything. So our formula at this point is 750 e to the 4 ln 2 all over 31 times t. So you could plug in 10. You'll have 750 e to the 4 ln 2 all over 31 times 10. And in the calculator, that's approximately $1,834.37 after 10 years. Okay. So it's a mathematical model. It's the cheapest mathematical model, and it's a model that everybody should know about. The next model is the Newton's law of cooling model. Let me maybe make a new section here. This is a section 2. This is section 3. Newton's law of cooling. So this is important if you maybe work in a foundry and you're doing castings or something like that. So you build, probably even with 3D printing now. So I was just watching this video the other day where they were 3D printing concrete, and it's freaking nuts. There's a lot of, you have to keep the concrete that's flowing through the 3D printer pen liquid. So it takes heat, and you don't want that stuff gucking up your 3D printer machine. And these are huge 3D printers, right? These are printers that are the size of a room. So they're hoping that they can 3D print these objects and then make a building out of them. I don't know what they think. But there's issues with cooling. You want it to come out smushy. You don't want it to cook up your machine. Other times, a long time ago, it was really, really cold out, and there was this experiment where you could take your water and then boil it and take it out. Please do not do this. You boil water, then you go outside and you throw it up in the air away from your body, and it freezes before it hits the ground. That's kind of more of a better sort of understanding representation than the 3D printing pen. But the deal is that the rate of change of the temperature of the object, so we call it something like T prime, is proportional to the difference between the surrounding medium of the object and the object's temperature, the temperature of the surrounding medium and the object's temperature. Okay, so let me write that out in words. And I mean, this is how you can build your own models. You just literally say it out in words, and then you write down the differential equation. So anyways, the rate of change change of temperature of object at some time t is proportional to the difference between the temperature of the object and the temperature of the surrounding medium. So the surrounding medium could be air in our case. So when you boil water and then you take it outside and it's freezing out, there's a huge difference between the temperature of the water and the temperature of the air, okay? And that means that the temperature of the water is going to change extremely quickly once you throw that water into the air. And what they say is it changes temperature so quickly that it actually freezes before it hit the ground. Okay, and I did try it. Please don't try it. Just go on YouTube. There's some idiot out there who's done everything imaginable, and you could kind of watch them do it. Please don't do that. Don't get burnt. Okay. So anyways, there's also the pizza problem. So if you take classes, you know, how long until my pizza is cold and I can't sell it to customers anymore, that sort of thing. Anyways, let's look at a problem from the book. Let's see where we are. 6.2 somewhere. Let's see what they had for us. This is an older book, so it may not be in your book. Okay, they're doing more like a some sort of foundry type thing. So they're removing an object from a furnace and they're placing it in an environment with a constant temperature of 80 degrees. Okay, so in their model, T prime equals K times T minus 80. And then its core temperature is 1500 degrees Fahrenheit. So that's initial temperature. So at time 0, the temperature of the object is 1500. 1 hour later, after it's removed, the core temperature is 11,120 degrees Fahrenheit. Okay, so after 1 hour, the temperature is 1,120 degrees Fahrenheit. Find the core temperature 5 hours after the object is removed from the furnace. So they want you to figure out the T value in 5 hours. Okay, so we have to solve this thing for T, big T. So I'm going to kind of separate it again, like I've been doing here previously. It's a lot like an exponential growth equation, except it has that minus 80. Otherwise, it would be exactly the same, right? Anyways, bring the little dt to the other side, divide both sides by t minus 80. Okay, so I have k dt. Integrate both sides, and we're going to get the ln of the absolute value of t minus 80 equals k times t plus the integration constant. Exponentiate both sides, and then you're ending up with absolute value of t minus 80 equals e to the c times e to the kt. Drop the absolute value signs, replace with a big constant. So you get c e to the kt, and then move the 80 to the other side. E to the kt plus 80. Okay. Now we need to kind of track down the initial value, the C. We got to figure out what C is. We got to figure out what K is. Okay. You can't just put 1500 in for C. It won't work that way. The C is not the initial value in the Newton's equation. So I need to plug in this first ordered pair, 0, 1500. Okay, so t will be 1500 when t is 0, so when little t is 0. So e to the k times 0 is e to the 0, e to the 0 is 1, and then plus 80. And you see c is not 1500, right? It's 1420. Okay. And then I have to use the other ordered pair to get the growth constant, the k value. Okay, so I have my equation as it is, 1420 e to the kt plus 80, and I'm going to put in the second ordered pair, so that'd be 1120 equals 1420 e to the 1 times k is k plus 80. And then I move the 80 over, so I have 1420 e to the k equals, I'll screw this up, what is it, 1040? Then divide both sides by the 1420 and simplify maybe a little bit. I think it's 52 all over 71, and so 104, 142, so 2 goes into that, 5, 2, 2 goes into this, 7, 1, yeah, and then take ln's on both sides, so you get k equals ln of 52/71, all in parentheses there. So now I have my sort of official temperature equation. So at any time t, I can get, an idea of what the temperature of this object is going to be. ln of 52 over 71 t plus 80. Okay. So in particular, they want to know the temperature at 5 hours. So you just plug in 5 for t, and you should have your answer. Times 5 plus 80, and I got approximately 379.2 degrees Fahrenheit. Okay, so that's the idea. We give you 2 models. The first model, definitely you got to have memorized. The second model, not so much. It usually comes up in differential equations if you take the actual class. There is a class in differential equations. If you're an engineer or if you're a math major, you'll be studying that more. But that's about the big and the small of it. Okay, so let's stop right there. Oh, I did not give you a quiz this time. Let me go back here and give you some sort of quiz. Oh, jeez. Sure, let's just have you solve an exponential kind of growth equation. Oh gosh, that wasn't it. So just solve this guy, dy over dt equals, and I want to see the work, right? So k times y. Okay, where your initial population is 5, and then your later population is 10, right? So I'll go ahead and kind of, so you got to separate the thing, and I got to see all your work. Let's put the dt over here, get the y over here, integrate. So we have ln absolute value of y equals kt plus c. And then we have to exponentiate. So absolute value of y equals either c times either the kt. I want to see all of your work. Drop the absolute values. The c e to the kt. I even want to see that. Replace. KT. Now I want you to get the equation. So we want to know basically at the end how much is there after 3 time units. Okay. So in this case 0, 5. So y of 0 is 5, right? So 5 equals c e to the 0, which tells me c is 5. Okay. And then I have to use this other initial condition, 2 comma 10, to get the k value. So right now my formula is 5e to the kt. So now I put in 10 for y, and I have 5e to the 2k. Divide both sides by 5, I get 2 equals e to the 2k, ln on both sides. So I get 2k equals ln 2, so I get k equals ln 2 over 2. So my equation, y equals 5e to the ln of 2 over 2t. And then I want to know what is y of, what did we say, 3? Okay. So you just plug 3 in for t, and let me do that on my calculator. 5 times e to the ln of 2 by 2 times 3 is 14 point something. So you're going to end up with 14.1 approximately, I think. So, check my work, make sure I didn't make any mistakes. Let me know in the comments if I did. And that's the quiz question for 6.2. Okay? Alrighty then, we'll see you next time.